is exactly some of the things I was going to touch on as well. My research so far has been much more focused on the, how do we look at trends across many species at once? So that's sort of most of what I'll be talking about today. And I'm focused in particular in the beginning, sort of how do we even detect that a range shift is happening, and how do we make sense of that? And then I'll talk a little bit about how to model at the end, but there wasn't as much what I was going to focus on. Just one second. Okay, so I guess I wanted to start out. You may have already covered these things, but at least when I think about sort of a species range that's shifting, there are a bunch of different demographic processes that happen in different places. There's colonization, one range edge that involves not only dispersal but also growth and reproduction in a new place. At the other range edge, there may be extirpation, mortality, or less reproduction, just so that population growth rates are, and population abundance is slowly going down. There may also be mobility, especially for more mobile marine species. They just may be adults moving out of a particular region. And yet, even without extirpation or colonization, is this coming through? Sorry, I can't tell if my microphone's working.
Yeah.
Okay, sorry, thanks. You can also have just differential growth or movement within an existing species range. So a shift in the location of biomass, but no change in range edges. So different demographic processes, though, underlying each of these kinds of changes. They don't all have to happen at once. It could just be one or a couple that happen for any given species. So if we sort of just use the Northeast US as an example, Canada up top, North Carolina down the bottom. It's about 1,200 kilometer section of coastline we're looking at here. In this case, red shows high biomass of black sea bass. This was 1967 from the Northeast Fisheries Science Center bottom trawl surveys, and then this was 2014. So if we're trying to think about how to summarize this, we could, some of the work I showed, but yesterday was just in terms of a centroid, right? It's just the average latitude of the biomass in this survey. You can also think in terms of that leading edge and how has that moved through space. Trailing edge doesn't show up for this particular species in this survey, but for some species it does. This one's somewhere down south of North Carolina. You can also think in sort of more complex, just what is that empirical distribution of biomass across latitudes or depth or long or coastline. You can sort of make a nonlinear line along a isobath along the coastline. Or even within a given area, which maybe is more relevant for sort of community dynamics or even for fisheries in a particular place. You can think about area occupied within a particular region, which may change through time. And each of these summaries of a distribution, I was going to talk about how to calculate them. So, for the Northeast US, this is just a map of all the survey points over the last, this is about 40 years of surveys. There are about 200 points that end up being surveyed in a given year. They actually get surveyed twice a year. But the way this survey and at least many surveys in the US are organized, in North America are organized, is that they have survey strata. So every time they go out and survey, they hit one or more points within each of these strata. And the number of points within each strata is designed based on the variance that they've calculated based on historical data, and as well as stratum area. So if we look across all the surveys that I showed you some data from yesterday, get a sense for sort of what the spatial footprints of these surveys look like. Eastern Bering Sea stands out as an area. They do actually have strata, but it's rather than a stratified random design, it's a stratified fixed design. So they go back to the same points every year rather than a random point within each strata. So in terms of actually calculating these sort of summaries of a species range, we have weighted average latitude of biomass, or you can do it in terms of presence. The edge is a bit tricky. You can look at the minimum or maximum latitude or depth, or if you're interested in movements across longitude, you can look at those edges. And yet, those tend to be quite noisy because it's quite a stochastic process whether you actually sample a species. So we often used summaries of edges like the 1st or the 5th percentile of species biomass or of species presence. Those tend to be a bit less affected by noise, but still, you're not capturing the absolute edge, which is almost impossible to survey with any confidence. Area, we can calculate one way to do it is the proportion of grid cells that are occupying a sort of pick a particular scale, or you can do percent volume contours, like the 90th, what percent volume contour captures 90% of the biomass or of the presence observations. And then each of these metrics, though, tells us something different. Tells us about different ecological processes. So the leading edge is telling us about colonization, the trailing edge telling us about extirpation, and different species characteristics, different ecological and demographic processes would be driving changes at these two different range edges. The centroid, in some ways, is useful because it pulls together many different kinds of demographic processes, and in some ways is really a pain to look at because, again, it pulls together so many demographic processes. It's hard to tease apart just from looking at centroids what's actually going on. Empirical distribution, again, captures all of those processes together as those areas of certain things. Just to show you one example for black sea bass, the blue line is the maximum latitude in this case of observation, and you can see how that's slowly shifted north over the last 40 years or so. The centroid is in black. You can see that also slowly shifted north. Whereas the southern range limit in this particular survey has that red line, but it's just at the southern limit of the survey, so which I plotted as that gray dotted line. So we have, in this case, we don't have any confidence that we actually see the southern range limit of black sea bass. We can look for temporal trends in these metrics over time. You can also look at interannual variability, whether that's related to environmental variability as well. There are also some metrics like stochastic dominance or empirical distribution functions to test whether an empirical distribution function from 1 year or set of years is closer to poles than another set of empirical distribution functions. One challenge that we run into quite a bit, though, is that surveys are tricky to do. They don't always hit. They don't always get every stratum that they wanted to get to every single year. There are equipment problems. There's bad weather. So if we look at the Northeast U.S., there's sort of this whole block. Every single stratum ordered from north to south is on this vertical axis. And then the years of the survey are across the horizontal axis, and some things become pretty clear. In the very first years of the survey, they went a lot further south than they do now. So one of the things in some of the work I showed you yesterday, we trimmed out all those southern strata. But then in recent years, it's also been tricky. You can see that they started skipping a number of strata. And 2014 in particular, they didn't go very far south at all. You can see it's all those white grid boxes. So you can trim those out. There's only so far, though, that trimming can go, especially if you think about a survey that goes on long enough. Eventually, almost every stratum has been missed at some point in time. And that makes it hard just to trim your way out of this problem. So Jim Thorson, I think, will be talking next about using model-based methods to infer empirically these kinds of metrics from imperfect survey data that have survey footprints that change a bit through time. So inferring center of gravity, area occupied, and edges of species distributions. It's been especially useful on the west coast of the US, where the survey changed survey design quite dramatically, actually, right around 2004 or so. provides a way to link those two surveys together. The last thing I wanted to talk about was connecting distribution to environmental change. So the stuff that John was talking about there at the end. And that is, a huge question. There's so much really interesting research to go into this and what are the key environmental factors. The species distribution models, at least that we've used, have been two-stage generalized additive models, where we think about a first stage that models presence and absence at a location time I and time t as a smooth function of the environment for location I at time t. And then we also combine maybe many environmental terms there, as well as a function of the survey. We've done a lot of work trying to combine across different surveys in the Northeast US. So we've included, at least so far, just a fixed effect for surveys. Some surveys are more effective at capturing a given species than others. And in this case, a binomial error term. And then the second stage of the generalized additive model is a model log biomass conditional on it being present. So this is only when biomass is greater than 0. Again, as a function of environment survey and now normally distributed errors. There are some potentially new error terms that allow us to do this just as one model rather than as two-stage. But we haven't used them yet. In terms of the environmental factors that we've been looking at so far, we've been looking at bottom temperature in a given location, minimum bottom temperature for a given location over the past year. So we've used oceanographic reanalysis products to reconstruct not only the temperature at a given place, but also what the temperature was in each month previously. So we can get minimum and maximum bottom temperature for a given location from the previous year. Similar seasonal SST, maximum SST. We actually didn't, in the work we published this summer, we didn't use minimum SST because it was very closely correlated with minimum bottom temperature. And then we also include metrics of bottom habitat, so seafloor rugosity and sediment grain size. Those two don't change through time, and so don't get matched to the particular year of the survey, just the location, whereas the other 5 factors are specific to a particular survey moment as well as location. And that's actually quite a bit different than a lot of the species distribution models that have been used on land, where it's just, we saw species at this location, what is the average climate at that location, averaging across lots of years. But I think, especially for marine species that are responding quite quickly to environmental variability, it actually provides us more power if we can look at the annually resolved or even monthly resolved environmental conditions at the time of observation. We don't include depth. When we've done tests, sort of taking some of the data, fitting models, and then comparing them against other years, sort of reserved observations, when we include depth as a factor, the models don't predict shifts in species habitat across depth very effectively, and yet we often see species shifting deeper or shallower. So we've actually left depth out of the models. Sort of all the surveys together that we've combined together. We do separate model. We've done separate models for Atlantic and Pacific. And to just the map on the left there shows that's actually, I believe that's rugosity, and then temperature, fit smooth functions for those, and then come up with species habitat projection. And I briefly mentioned this at the end of John's talk, but we've seen, in some cases we know pretty clearly why, they seem to be working pretty well for some species. In other cases, they seem to be really falling down. The benefit of this approach is we can apply it across hundreds of species all at once. It's sort of useful first cut, even though it misses a lot of the mechanism that for some species is really important. For a species like gray snapper, for example, we predict a much we predict a poleward distribution that extends too far to the north. And that's in part because this is a species that overwinters in estuaries, and that estuary temperature sets the northern limit of the adult population as well. They come out from the estuary and move out onto the continental shelf. And so we actually, the species distribution model like this doesn't predict that gray snapper would be close to the coast. It actually gets the northern range limit on the coast about right. But then there's offshore habitat that looks like it would be suitable for adults. And right, because these correlational models aren't including, we could include, in this sort of many species approach, we didn't include the estuarine temperature at the same latitude as a given grid cell offshore. It doesn't capture that movement between habitats. Whereas thinking mechanistically and more carefully about each individual species, you could include that detail, either in a more mechanistic process-based model or actually even in a correlational model like this. Some of the other assumptions that I think are important to think about are that they're modeling habitat, not spatial population dynamics. There are lots of things that affect population size, including fishing and interaction with other species. And they're modeling a realized population niche in the field. So that accounts for interactions with other species, it accounts for multiple environmental factors all at once, which may be very different than a fundamental niche that you would measure in the lab. And therefore, making that, as came up in the discussion, making that transfer from a fundamental niche we measure in the lab to the realized niche in the field may be dramatically different. Actually, I think in many cases, it's going to be a very difficult research problem to go from physiological limits in the lab out to species distributions in the field. One of the other assumptions is that the observations and the species distributions are in equilibrium with the environment. And yet, if the environment changes quickly, where species are found at a given moment may actually be out of equilibrium with the environment. And so we can talk about some ideas on how to attack that problem next. But that is one of the assumptions. For species that are quite mobile, though, their distributions may more or less be in equilibrium with the environment. It may be an okay assumption. And the other big assumption is that the environmental relationships stay the same through time. And that, in effect, means that we're assuming that species interactions are staying the same, that influence, and that includes influence of fishing. If fishing is extirpating species from a given area, or recovery from fishing is letting them expand into a new area, that would change the relationship between species distribution and the environment in a way that these static statistical models do not account for. And then the last thing I want to mention that I touched on a little bit yesterday is that right now we're moving towards dynamic range models, which I think are an interesting hybrid between really intensely mechanistic models for single species and these very correlative statistical models for many species all at once. The idea is that we model the population dynamics. We've started out just thinking about sort of 3 size classes and transitions between those size classes and recruitment and movement across space. And using surveys that include size data, where they're measuring fish length, not just biomass, we can then actually fit these process-based models against the observations from the bottom trawl surveys, and using methods like approximate Bayesian computation, though it's not the only method that's out there. So right now, this I think is a really useful tool to move towards, and we're trying to test out the methods right now in the Northeast US. So maybe I'll leave it there and happy to take some questions if there's time. Oops. There.
Where's the microphone?
Yeah. It's a comment really, I guess. And we focused a lot on species. Thanks, Byron. That was a very nice talk, and you make some very valid points about the species distribution modelling. And I think that's relevant for two cases where we want to forecast clearly because we don't have any data to look back to, or where we are in a data poor situation where we have big gaps. But even then, you know, there are quite a lot of scenarios. Mackerel is an exception, which is not one, but there are quite a lot of scenarios where we have contained empirical information. And quite often, regardless of SDM type analyses, there's a big enough debate about estimation, full stop, in terms of the various statistical models to estimate the quantity. So even within ICES, for example, to come up with our estimates of index at age, you know, it is not very conclusive as to how to deal with some of the extreme value problems that we have. So I've seen data sets where, you know, large cod trawls are just chucked out, and that's called a Windsorized mean in statistical terms, and it makes a massive, massive difference. Not only to the biomass estimate, which is why it's done, because it's hard to deal with, but also to a lot of these statistics, which are looking at distribution changes because the centroid is weighted to that way or not. So, I mean, SDMs are great for those two periods, but I think there's also a sort of component of analysis of the empirical data, which in many respects is just as important for thinking about what has happened, what distribution changes have occurred.
Yeah, I have a comment on that too.
Totally.
Oh, sorry, go ahead, Matt.
I just make maybe one small follow-up comment. I totally agree. And you know, maybe that's in part, you know, I focused on the empirical analysis in the beginning. We have found that, at least from the modeling species habitat, our models based just on presence for some species look quite a bit better than the models based on both presence and biomass. So there may be some reason to actually simplify down to presence, even though we're throwing out data. But part of that, I think, has to do with the extreme value problem that you're talking about.
Yeah, my comment was, you know, it seems like when you project these things into the future, you typically have some model of how the climate's going to change. You know, whether that's downscale or from a global climate model. You know, and that adds another layer of uncertainty into these projections too. You know, it seems like one of the things I've been seeing in papers is that people are kind of advocating for don't just present the results, but present the uncertainties around those results too, and not only the uncertainties, but the uncertainty at each kind of stage of the process in your projections.
Yes, that's something we've been spending a bunch of time thinking about. You know, different not only actually GAMs I showed you here, but also generalized linear models, boosted regression trees. You know, can we set for the suite of models, sample from the parameter uncertainty in those models, sample from uncertainty across global climate change, global climate models, and uncertainty across climate scenarios, representative concentration pathways.
Hi, Nealon, it's Joey again.
Hey, Joey.
Hi, so my question is related to a slide that you had on assumptions, and you mentioned this challenge of scaling from lab studies out to the field, and this idea that we're measuring, in the lab we're measuring the fundamental niche, but what we're observing in the field is the realized niche. And I just wanted to clarify, it seems to me that with your approach, you're not, like, you're in you know, predicting or explaining abundance or presence absence as a function of field conditions. You're not using lab temperature preferences, so you're effectively basing your predictions on realized niches, not fundamental niches, unless I misunderstood something. Is that right?
Oh, yeah, sorry that was unclear. That was more just me picking up on part of the conversation after John's talk.
Okay,
Yeah,
cool.
no,
Okay.
what we pick up from the field is realized, not fundamental at all.
Right, okay. And just maybe a related question is, has anybody used the type of data that you have on these realized niches and compared them to fundamental niches that we generate in the lab?
Well, one person who's done a bit of that is Jennifer Sunday, right? You know, looking at whether marine species overfill their fundamental niche based on physiological studies.
Right.
And the interesting thing there, right, was actually on average marine species don't underfill or overfill, which actually is very surprising. So I think there's still more work to be done to sort of figure out what's going on. That maybe marine species are closer to their, maybe the realized niche is closer to their fundamental niche, at least as compared to terrestrials.
Cool, thanks, Bill.
Hello, Malin. This is Tom Helser speaking. You probably don't know me. So it was interesting that you said that the presence-absence data were generally fit better than the abundance data. And I just wonder if you might not want to consider two covariant structures that you don't have explicitly integrated into your model. One is that what you're actually fitting with both of those is density, and the density is the product of the probability of being present times the abundance, or the CPUE, given that it's non-zero, right?
Mm-hmm.
So I've done a lot of this work, and I've looked at the relationship of the proportion so if you take all your strata and look at the correlation between the proportion non-zero and abundance, you'll find that they're positively correlated.
Right, yeah.
And so, there's two ways to do that. One is to build in a model that explicitly deals with that covariant structure, or uses zero-inflated Poisson or something like that. The other thing is you might want to include an autoregressive spatial structure in the error term that would basically account for abundances or densities having some sort of area-specific relationship.
Yeah, no, both good points. We have looked at things like zero-inflated Poissons, and they don't tend to fit as well, at least when we've looked at it.
Yeah,
which
probably
is part
because
of
of
why
over dispersion problems.
Yeah, why we've broken it apart like this, but there are, recently learned about an error distribution that is supposed to work better, and I'm blanking on what it's called, starts with W. Someone, you may know it off the top of your head, and I'm just forgetting.
I do know it, and it's not reliable, it's something else. But the other opportunity actually to try to do some work is to try this in a Bayesian framework.
Mm-hmm.
Because I think the Bayesian framework will allow you to assess the goodness of fit a lot better than, say, using a likelihood or whatever you're using as the optimization. Because you can calculate the significant tail probabilities and look at whether or not the fit of the model is consistent with the empirical data.
Yeah, I mean, we definitely, we do sort of, leave aside part of the data and then compare the predictions against the data that's been held out. But I agree. I mean, there are a lot of really interesting new methods that can be used. But I think your point about the error distribution is an especially good one. The data from these surveys do tend to be tricky. They're often clumped in space, so there are spatial autocorrelation issues. And you tend to, if you get some, you tend to get a lot. So they're zero-inflated and also have really extreme high values as well.
Thank you.
Great points.
I have a comment. It'd be interesting in hearing kind of your thoughts on this, but so you presented a kind of a range of tools, ranging from really kind of model-free empirical examinations of your data, all the way to some statistical models that were pretty sophisticated. It seems like that's a good way to think about it. I mean, there's like some people might argue that we should just use kind of model-based estimates of these kind of things, but I think there's some value of kind of the empirical distribution or descriptions of the data as well. It seems like these are methods that are different methods have different strengths and weaknesses, and by having kind of an ensemble approach, you can kind of pick up different information.
Yeah, no, entirely. I mean, I think that's why I presented this. I think there's an enormous amount we can learn just about trying to understand what has happened.
Right, exactly.
It's happened, and but then then there's the next step of do you want relatively simple statistical models, though they can still be very sophisticated, so it's statistical correlation models, or do you want to move all the way up to more mechanistic models, and then obviously go even further than I talked about. John in his last talk was talking about individual-based models as well. Right. So I think this range of tools, and a lot of it Depends on, are you really interested in what's happening in one species in one location and can really dive into the details, or you're trying to describe changes across many species in many locations? So
Right.
we have a set of tools that are each going to be suitable in different places and different questions.
Right. Well, I was thinking, especially like the, the centers of gravity and the area occupied that are computed directly from survey data without a model. I think it seems to me that if you appropriately account for the survey design, those can be really useful tools. And of course, there's advantages to being model free as well. I mean, then you don't have to worry about distributions. You're just tracking your data. So.
Exactly.